The ability of Python to allow you to use broadcasting operations, and more generally, the great flexibility of the Python numpy programming language is, I think, both a strength as well as a weakness of the programming language. I think it's a strength because the great expressivity of the language, the great flexibility of the language lets you get a lot done, with even just a single line of code. But it's also a weakness because with broadcasting and this great amount of flexibility, sometimes it's possible you can introduce very subtle bugs or very strange looking bugs if you aren't familiar with all of the intricacies of how broadcasting and how features like broadcasting work. For example, if you take a column vector and add it to a row vector, you might expect it to throw up a dimension mismatch or type error or something. But you might actually get back a matrix as a sum of a row vector and a column vector. So there is an internal logic to these strange effects of Python, but if you aren't familiar with Python, now I've seen some students have very strange, very hard to find bugs. So what I want to do in this video is share with you a couple of tips and tricks that have been very useful for me to eliminate or simplify and eliminate a lot of the strange looking bugs in my own code. And I hope that with these tips and tricks, you also be able to much more easily write bug-free Python and NumPy code. To illustrate one of the less intuitive effects of Python NumPy, especially how you construct vectors in Python NumPy, let me do a quick demo. Let's say I set a equals np.random.randn5. So this creates a 5 random Gaussian variables stored in an array A. And so let's print A. And now it turns out that the shape of A, when you do this, is this 5 comma structure. And so this is called a rank 1 array in Python, and it's neither a row vector nor a column vector. And this leads it to have some slightly non-intuitive effects. So for example, if I print A transpose, it ends up looking the same as A. So A and A transpose end up looking the same. And if I print the inner product between A and A transpose, you might think A times A transpose is maybe the outer product, should give you a matrix maybe. But if I do that, you instead get back a number. So what I would recommend is that when you're coding neural networks, that you just not use data structures where the shape is this 5 comma or n comma rank 1 array. Instead, if you set A to be this 5 by 1, then this commits A to be a 5 by 1 column vector. And whereas previously A and A transpose look the same, if you now print A transpose, now A transpose is a row vector. Notice one subtle difference. In this data structure, there are 2 square brackets when you print A transpose, whereas previously there was 1 square bracket. So that's the difference between this is really a 1 by 5 matrix versus one of these are rank 1 arrays. And if you print, say, the product between A and A transpose, then this gives you the outer product of a vector, right? And so the outer product of a vector gives you a matrix. So let's look in greater detail at what we just saw here. The first command that we ran just now was this, and this created a data structure where A.shape was this funny thing 5 comma, and so this is called a rank 1 array. And this is a very funny data structure. It doesn't behave consistently as either a row vector nor a column vector, which makes some of its effects non-intuitive. So what I'm going to recommend is that when you're doing your programming exercises, or in fact when you're implementing logistic regression or neural networks, that you just do not use these rank 1 arrays. Instead, if every time you create an array, you commit to making it either a column vector, so this creates a 5 by 1 vector, or commit to making it a row vector, then the behavior of your vectors will maybe easier to understand. So in this case, A.shape is going to be equal to 5 comma 1, and so this behaves a lot like or in fact this is a column vector. And that's why you can think of this as a 5 by 1 matrix or as a column vector. And here, A.shape is going to be 1 comma 5, and this behaves consistently as a row vector. So when you need a vector, I would say either use this or this, but not a rank 1 array. One more thing that I do a lot in my code is if I'm not entirely sure what's the dimension of one of my vectors, I'll often throw in an assertion statement like this to make sure in this case that this is a 5 by 1 vector, so this is a column vector. These assertions are really inexpensive to execute, and they also help to serve as documentation for your code. So don't hesitate to throw in assertion statements like this whenever you feel like it. And then finally, if for some reason you do end up with a rank 1 array, you can reshape this, a equals a dot reshape, into say a 5 by 1 array or a 1 by 5 array, so that it behaves more consistently as either a column vector or a row vector. So I've sometimes seen students end up with very hard to track down bugs because of some of the non-intuitive effects of rank 1 arrays. By eliminating rank 1 arrays in my own code, I think my code became simpler, and I did not actually find it restrictive in terms of things I could express in code to just never use a rank 1 array. And so takeaways are, to simplify your code, don't use rank 1 arrays. Always use either n by 1 matrices, basically column vectors, or 1 by n matrices, or basically row vectors. Feel free to toss a lot of assertion statements to double check the dimensions of your matrices and arrays, and also don't be shy about calling the reshape operation to make sure that your matrices or your vectors are the dimension that you need it to be. So I hope that this set of suggestions helps you to eliminate a class of bugs that from Python code and makes the programming exercise easier for you to complete.